Hi everyone, this is Group 3. Our topic is C-Storms, a column-oriented database management system. There are four group members in our group: Haoran, Yiqi, Xiaohang, and Tianqi. Below is a task allocation. Our topic focuses on the design of a column storm called C-Storm. It represents a class of rate-optimized system. It is more efficient that the value of each single columns are stored consciously. Using a column storage architecture, the database management systems only needs to process a given query to read the required column values and avoids the irrelevant attributes into memory. Why is System more efficient? Current relational database management systems were designed to store values in their native data format. It was too expensive to ship data values onto bytes or word boundaries in main memory for processing. Hence, the CPU cycles trade-off is profitable in the read-mostly environment because CPUs are getting faster than disk bandwidth. There are two ways of using CPU cycles to save this bandwidth. First, it can code data elements into a more compact form. Second, it shoots dense pack values in storage. System physically stores a collection of columns, each sorted on some attributes. Groups of columns sorted on the same attributes are referred to as projections. The same columns may exist in multiple projections, possibly stored on the different attributes in each. Why does warehouse system use copy of the data? They maintain copies of data because the cost of recovering through database management system login processing on the large data is too high. This option is attractive because of the declining cost per byte of disks. It is not required to store multiple copies in the exact same way. System allows redundant objects to be stored in the different sort orders. In the mostly environments, warehouses also need to perform online updates to correct errors. Also, there is a tension between providing updates and optimizing data structures for reading. For example, columns of the data are maintained in entry sequence order. This allows efficient insertion of new data items at the end of the column. The cost is less than optimal retrieval structures because most queries workloads will run faster with the data in some other orders. However, storing columns in non-entries sequence will make insertions very difficult and expensive. As we're focusing on these problems, we combine in a single piece of system software both a rate-optimized column store and an update-oriented writable store connected by a tuple mover. WS is architected to support high performance inserted and updates. RS is optimized for read and support only a very strict form of insert. Queries must access data in both storage systems. Inserts are sent to WS, while deletes must be marked in RS for later purging by the tuple mover. So updates are implemented as an insert and delete. This is an example of the data model. The two tables above are logical tables. In System, the logical tables does not store data. It is used to provide the schema of the query. The data in System are stored in several projections associated with the logical table. The following three forms are projections. So projections sorted by one or more columns enabling more efficient compression and faster querying. Sometimes a query may require multiple projections in the same logical table to complete. So System supports constructing multiple projections columns into a single record. So this operation is called tuple construction. The logic of the tuple construction is to record the line number of each value, then record a table called join index between the two projections and tell the two projections how to join. So next, each will talk more about write-optimized store and the read-optimized.
Okay. The third part is readable storage, writable storage, and tuple mover. Readable storage is read-optimized colon store. The encoding chosen for colon depends on its order. Let's describe its encodings below. Type 1 encoding is represented by tuple's value, position, and number. Moreover, the height of index which large blocks gives small. Type 2. Every value in type 2 in a column adds a delta from the previous value in the column. Type 3 is represented by tuple's value. V is a value stored in a column, and B is a bitmap indicating the positions which is stored, and value in type 4 don't have to be encoded. Writable storage support for write. Compared with readable storage, writable storage has less data, so data don't have to compress. The update data for each column in the projection is represented by a pair, value storage key, and a B-tree is beautiful storage key. The ace in the projection is represented by an addition pair, stored key value first occurs storage key, and a B-tree is established by stored key value. Additionally, the job of tuple mover is move blocks of tuples from writable storage to readable storage by deleting tuples which delete on writable storage and inserting tuples which insert on writable storage. And join indexes is to connect projection anchored at the same table. We have to pay attention that writable storage and readable storage must be integrated. After move and join tuples, next step is storage management. In using storage allocator to allocate segment of nodes in a grid system, there are some points we should pay attention to. All columns in a single segment of a projection should be co-located, and each writable storage segment will be co-located with the readable storage segment that contain the same key range. I think simply the representation of a collection of columns. And Xiaohang will introduce next part.
Hi there. Let's talk about the updates and transactions. The C-store is designed for read transaction, but also support the write transaction. Therefore, C-store applies different strategies for different transactions. The C-store applies the snapshot isolation to deal with the read-only transactions. So why snapshot isolation? One important reason is that we do not need this to set any locks. The snapshot isolation works by allowing read-only transactions to access the database as of some time in the recent part, before which we can guarantee that there are no uncommitted transactions. For this reason, when using snapshot isolation, we do not need to set any locks. And how it works? The C-store designs and maintains two global timestamps, the high watermark and low watermark. A low watermark is the earliest effective time at which a read-only transaction can run, and we call the most recent time in the past at which snapshot isolation can run the high watermark, and is maintained by the time authority. C-store allows the user to query at any timestamp between the high watermark and low watermark. For the read-only transaction, the C-store applies traditional two-phase locking, and it's also worth noting that in C-store, the distributed commit code differs from two-phase commit, because the master in transaction of C-store does not prepare the worker side. When it comes to the C-store query execution, The query operators in C-store is quite similar with the traditional SQL operations, and the main operators include decomprise, select, mask, and so on. The main difference is that the bitstring operators based on bitmap to field data, and the query optimization. The C-store uses a cylinder-style optimizer that uses cost-based estimation for plan construction, and the major optimizer decision is which set of the projections to use for a given query. And let's now move to the Tinty's part.
Hi everybody, let's start the most interesting part, the comparison between three different systems. Well, because WS and Tuple Mover are not at the point where we can run experiments on, and RS also does not support segments or multiple grid nodes, our comparison is based on read-only queries performs on RS running in single sites. Our benchmarking system is a 3 GHz processor with 2 GB memory and 750 GB of disk. Here we use a simplified version of TPCH, which is a decision support benchmark, to reflect the capability of the system to process queries. If you remember, we have introduced full comparison method of digital processing in the previous chapter. Therefore, our test is based on column with type integers. So we tested three systems, which is a C store system, and another two systems implements a row store and a column store. Our test divides into two parts, the disk usage and the time measurement of 7 queries. Here's the result of our test. As you can see from the graph, C-store takes the least space usage and the shortest time cost for a query. And in order to give the other system, especially the row store, some possible advantage, we try to running them with the materialized view that correspond to the projections we used with C-store. And we try the previous two tests again. Here we take the test result from the materialized view, and C-store still has its advantage. So according to our article, for the case of unconstrained space, C-store is 6.4 times faster than the commercial row store, but the row store takes 6 times the storage space. C-store is on average 16.5 times faster than the commercial column store, but the column store requires 1.83 times the storage space. It comes to the conclusion that C-store is better than the traditional row store and column store in average case on both storage space and processing speed. So finally, we come to our conclusion part. So this paper has presented the design of C-store, who aims at the read-most DBMS market. It has a radical departure from the architecture of current DBMSs. We conclude the features of C-store as follows. Firstly, it has a hybrid architecture with WS component optimized for frequent insert and update, and an RS component with an associated query execution engine optimized for query performance. The architecture allows transactions between components on a column store. And second feature is that because of the feature of column store, C-store heavily compressed columns using one of several coding schemes. Therefore, it saves the space usage for storage. And the third feature is that the system stores the redundant records of elements of a table in several overlapping projections in different orders, so that a query can be solved using the most advantage projection. The next feature is that it has a column-oriented optimizer and executor with different primitives than in row-oriented system. And shared nothing architecture is a grid environment in which there are G nodes, and each node has private disk and private memory. And the last feature is that the use of snapshot isolation is used to avoid 2PC and locking for queries. So we conclude that the main advantage for C-store is into two parts. Firstly, it provides faster of read query than column store and row store. And secondly, it saves storage space than the other two systems. So here's the references of our presentation. And thank you, everyone.